A single line in a spectrum, faint and redshifted, can overturn an entire cosmic origin story. That's the leverage of modern observational astronomy: precise, patient, and ruthless in exposing gaps in tidy narratives. Today, JWST's data have produced such a line and pushed a provocative question into the open. Could the first beacons of the universe have been powered not by fusion but by dark matter? So watch this video till the end and subscribe to the channel. Let's begin. The standard account that anchors nearly all of modern cosmology is compact and powerful. After the Big Bang, the universe cooled, leaving a nearly uniform sea of hydrogen and helium. Tiny density fluctuations grew under gravity. Gas collected into the first gravitational wells. When a collapsing cloud's core reached sufficient temperature and pressure, hydrogen fusion ignited and a star was born. Those first-generation stars, the so-called population 3 stars, are predicted to be metal-free, meaning composed almost entirely of hydrogen and helium, far more massive on average than today's stars, and extremely short-lived relative to low-mass stars like the Sun. They heat and ionize their surroundings, explode in violent supernovae, and seed the cosmos with the first heavy elements that allow later generations of stars, planets, and chemistry to form. This narrative, Big Bang, neutral gas, collapse, fusion, enrichment, galaxies and black holes, is the scaffolding of cosmic history used in cosmological models and in interpreting almost every observation of the early universe. Why this story is persuasive is worth stating plainly. Nuclear fusion is a known laboratory-tested physical process. The sequence predicts the appearance of the first elements and the chemical evolution we observe in later epochs. And it fits a huge body of indirect evidence from the cosmic microwave background, nucleosynthesis calculations, and the statistical distribution of galaxies. In short, it works, until it doesn't. For decades, theorists built detailed models of population 3 star formation that produced very massive stars, tens to a few hundreds of solar masses in many models, predicted extreme ultraviolet output, and anticipated rapid enrichment of the surrounding medium through supernovae or direct collapse to black holes. Observers therefore went looking for the signatures these models forecast. Very blue ultraviolet spectra at high redshift, strong ionizing photons, and, where available, traces of subsequent chemical enrichment. But problems accumulated as data improved. JWST and other instruments started to reveal objects in the first few 100 million years after the Big Bang whose luminosities, inferred masses, or implied black hole seeds were surprising. In some cases, seemingly too large or appearing too soon to be comfortably produced by the standard POP3 stellar evolution remnant pathway. Those tensions are not proof of a different mechanism, but they are the empirical cracks that invite alternative explanations. The essential point: the conventional picture is both robust and constrained. When multiple, independent observational lines point at an anomaly, unusually massive early objects, unexpectedly bright galaxies, or supermassive black holes at very high redshift, it is scientifically responsible to consider whether a missing ingredient might alter the first chapters of cosmic history. NASA's early universe summaries and review literature emphasize the central role of POP3 stars in rionization and enrichment, which is why any credible alternative must either reproduce those roles or show a path to the same end states by different physics. Two clarifying caveats before moving on. First, population 3 is a theoretical classification built to describe metal-free first-generation stars. Direct detection of an unequivocal POP3 star remains exceptionally difficult because they are rare, short-lived, and far away, though JWST's sensitivity was expressly designed to make that search feasible. Second, the standard story has flexibility. It admits a range of stellar masses, formation environments, and subsequent evolutionary paths, including direct collapse scenarios that produce massive black hole seeds without the usual supernova route. So, when we say the standard picture held, we mean that it reliably explains a wide range of observations, not that it is immune to revision in the face of new, robust anomalies. Where this chapter leaves us, the community entered the JWST era expecting to confirm and refine the population 3/fusion first narrative. That expectation is still the baseline, but the combination of JWST's deep infrared spectroscopy and surprising early findings exposed several why now puzzles. Objects whose brightness, inferred mass, or spectral features strain simple fusion-only models. Those tensions constitute the empirical motivation for more radical hypotheses, including the possibility that some of the earliest luminous objects were powered, at least in part, by non-nuclear processes. The conventional chain of reasoning, collapse, fusion, enrichment, remains the default, but the data now permit, and in some corners seem to demand, consideration of alternatives that would change what we mean by first light. Dark matter enters the story as the quiet but indispensable background, an invisible mass component first inferred nearly a century ago from galaxy rotation curves, cluster dynamics, and later from gravitational lensing and the large-scale distribution of galaxies. Its gravitational effects are unambiguous. Galaxies rotate too quickly at their edges to be held together by visible matter alone. Galaxy clusters exhibit velocities that require far more mass than their luminous contents supply. And the cosmic web itself forms in patterns that cannot arise unless most matter is non-luminous. Across all these probes, the numbers converge. Roughly 85% of the universe's matter is dark, non-radiative, and weakly interacting. Yet, despite its dominance, dark matter remains undetected by any laboratory experiment. It does not absorb light, does not emit it, and does not scatter it in ordinary ways. It reveals itself only through gravity. This invisibility masks a critical point. Gravity is not the only potential channel of influence. Many particle physics candidates for dark matter, especially WIMPs, weakly interacting massive particles, possess the possibility of self-annihilation, meaning that when two dark matter particles encounter each other, they could annihilate into standard model particles, releasing energy. On galactic scales today, the density is too low for annihilation to matter. But in the early universe, where matter was far more concentrated, annihilation rates could have been significantly higher. If annihilation occurs, it does more than convert mass to energy. It heats ordinary baryonic gas in the same region, injecting power directly into the medium. When theorists first calculated this possibility, they noted that the power density from annihilation in high-density mini-halos at early cosmic times could become comparable to, or even exceed, the heating from gravitational collapse. Under those circumstances, dark matter would not merely shape where the first stars formed. It could act as an internal heating source within the collapsing protostellar cloud. This is the origin of one of the most radical ideas in early universe astrophysics, that dark matter, normally treated as a passive scaffold, might have actively powered the first luminous objects. The logic is straightforward. Annihilation produces energy. The rate depends on the square of the density. Early mini-halos had high enough densities of dark matter, and baryonic collapse naturally funnels more material, both ordinary and dark, toward the center. If the annihilation heating rate balances or exceeds the cooling and collapse rate of the gas, the cloud could stall before reaching the conditions needed for nuclear ignition. Instead of collapsing into a compact fusion-powered star, the object could inflate into a giant, diffuse, long-lived body whose luminosity is supported by continuous annihilation within its core. This framework redefines what it means to be a star. Fusion is no longer required. The energy source shifts from nuclear processes to particle physics, and the relationship between mass, radius, luminosity, and lifetime changes dramatically. It also introduces a crisp observational possibility. Stars powered by dark matter would have temperatures, sizes, and spectral characteristics distinct from those of fusion stars. The appeal of this idea becomes clearer when viewed through the lens of cosmological problems that persist in standard models. One of the long-standing puzzles is the existence of supermassive black holes at extremely high redshifts, objects with masses of millions to billions of suns appearing only a few 100 million years after the Big Bang. Growing black holes of that size through ordinary stellar remnants requires time, fuel, and efficient accretion, conditions that seem difficult to satisfy so early. But if some early luminous objects were dark matter powered, their masses could grow to thousands or millions of solar masses without undergoing the rapid nuclear burning and violent deaths of typical stars. When their dark matter fuel is exhausted, such massive objects could collapse directly into black holes with enormous initial masses, providing natural seeds for the supermassive black holes observed by JWST and other instruments. This is not proof, but it is a coherent connection between an unexplained observation and a plausible physical mechanism. Beyond black holes, dark matter-powered heating offers a new pathway for early luminosity. If even a small population of such objects existed, they could contribute to reionization, influence the thermal state of the early intergalactic medium, and alter the ionizing photon budget in ways distinct from fusion stars. Because their surface temperatures are predicted to be lower, their spectra would be different, redder, more diffuse, possibly lacking metal lines, and dominated by hydrogen-helium signatures shaped by their inflated radii. And importantly, their sheer size, potentially hundreds to thousands of astronomical units, would give them luminosities rivaling small galaxies. In effect, dark matter becomes not only a gravitational architect, but a potential engine for the universe's earliest light. This is the conceptual groundwork. Dark matter is invisible, abundant, gravitationally dominant, and under certain particle physics models capable of annihilation that releases energy. The early universe had environments dense enough for this annihilation heating to become significant. And if heating exceeds cooling during protostellar collapse, the result is a new class of luminous objects not powered by fusion. These ideas stayed mostly theoretical for over a decade, waiting for data with the precision to test them. The possibility remained academically interesting, but observationally inaccessible, until JWST provided spectra from the first few 100 million years of cosmic history. The idea that dark matter might heat a forming star naturally led theorists to ask a deeper question. If that heating is sustained, what kind of object would actually emerge? This is where the modern dark star hypothesis took shape. In 2007 to 2009, researchers including Catherine Fries, Douglas Spollier, Paolo Gondolo, and their collaborators ran the first detailed calculations of how a collapsing primordial gas cloud behaves when immersed in a dense reservoir of self-annihilating dark matter. Their models showed that as baryonic gas collapses, it steepens the potential well at the center of a mini-halo and drags dark matter inward through a process known as adiabatic contraction. This increases the central dark matter density dramatically. Because annihilation rates scale with the square of that density, the heating grows rapidly as the collapse proceeds. Instead of collapsing into a compact protostar with temperatures high enough to ignite fusion, the cloud can stall, puff outward, and settle into a quasi-stable configuration supported almost entirely by annihilation heating. The object that results is unlike any star found in the later universe. In the original calculations, a dark star is predicted to be orders of magnitude larger in radius than typical fusion stars, potentially hundreds to thousands of astronomical units across. Despite this enormous size, the surface temperature remains relatively cool, somewhere in the range of a few thousand Kelvin, cooler than massive fusion stars that blaze at tens of thousands of Kelvin. Yet, because luminosity scales strongly with radius, these cool surfaces can still produce tremendous total light output. A dark star could shine as brightly as a galaxy while remaining diffuse enough to avoid the extreme ultraviolet signature of normal massive stars. In its core, temperatures stay too low to trigger hydrogen fusion. The object is held up not by thermal pressure from burning hydrogen, but by the continual injection of energy from dark matter annihilation. Mass and lifetime were the next revelations. Once stabilized by annihilation heating, a dark star could continue gathering baryonic matter from its surroundings. With fusion suppressed, it avoids the intense radiation pressure that limits the growth of ordinary massive stars. In the most extreme models, this allows dark stars to grow far beyond the usual stellar mass limits. Tens of thousands, millions, even up to 10 million solar masses in some simulations known as supermassive dark star scenarios. If dark matter annihilation persists, these giant objects could survive for hundreds of thousands or even millions of years. Longevity impossible for equivalently massive fusion stars, which burn through their fuel in extremely short timescales. This is where the hypothesis crossed from curiosity into a potentially profound cosmological mechanism. If these supermassive dark stars form and persist for long enough, they would act as enormous baryonic sinks in the early universe. When their annihilation fuel finally runs out, whether from dark matter depletion or dilution, they would collapse directly under their own gravity. A collapse from millions of solar masses leads naturally to the formation of a massive black hole seed, bypassing the slow accretion path required by ordinary stellar remnants. The existence of unexpectedly large black holes at high redshift, observed in the JWST era, suddenly had a plausible formation channel. Even before JWST launched, the dark star hypothesis had matured into a coherent family of models. Some versions relied mainly on the dark matter concentration created during collapse. Others introduced ongoing capture of dark matter particles scattering off baryons inside the star, though this depends sensitively on uncertain particle physics cross-sections. All versions agreed on the basic ingredients. Dark matter heating prevents fusion ignition, inflation leads to enormous radii, and slow evolution allows continuous mass growth. The predictions were distinctive: cool but luminous, metal-free spectra, large physical radii, and potential survival into epochs accessible to next-generation telescopes. Yet for all its elegance, the hypothesis remained untested. For more than a decade, dark stars existed only as theoretical constructs, waiting for observational data capable of probing the universe's earliest few hundred million years. Conventional telescopes lacked the infrared sensitivity and resolution needed to examine objects at redshifts greater than 10. There was no way to confirm or falsify the existence of these giant, dark matter-powered bodies. That observational barrier is precisely what the James Webb Space Telescope was built to overcome. the theoretical picture of dark stars would have remained an elegant footnote if not for a series of stubborn observational puzzles that accumulated long before JWST ever opened its sunshield. As astronomers pushed deeper into the universe with Hubble, ALMA, and ground-based surveys, they kept encountering objects in the early cosmos that didn't quite fit the neat POP3 to galaxy progression. These were not small discrepancies. They were structural tensions that hinted at missing physics in the standard narrative. One of the most striking gaps concerned supermassive black holes appearing far too early. Objects like quasar J 1, 3, 4, 2, plus 0, 9, 2, 8, discovered at redshift approximately 7.5, already contained black holes a billion times the mass of the Sun, when the universe was only approximately 690 million years old. JWST has since revealed even more massive candidates at even earlier epochs. Traditional growth pathways, starting from a approximately 100 solar mass POP3 remnant and expanding through accretion, struggle to reach such colossal sizes so quickly, even under optimistic assumptions of continuous near-Eddington accretion. Something had to accelerate the process or create larger seeds to begin with. Dark stars, if they grew to hundreds of thousands or millions of solar masses before collapsing, provide exactly the kind of heavy seed scenario that would allow these early giants to emerge naturally. Another tension involves the brightness of early galaxies. Even before JWST, some early universe galaxies appeared unexpectedly luminous. But JWST pushed the problem into a sharper, more surprising regime. Galaxies at redshifts 10 to 14, only 300 to 400 million years after the Big Bang, appear to host more stellar mass and to emit far more ultraviolet light than expected if their stars followed normal fusion rules. Standard models predict limited growth at such early times. Gas cooling is inefficient, metal-free stars burn fast, and feedback from radiation and supernovae should slow further star formation. Yet JWST found galaxies whose brightness resembles systems that should have taken hundreds of millions of years longer to assemble. If some of these early points of light are not traditional galaxies, but single supermassive objects, dark stars, they could easily account for the observed luminosity without demanding rapid, large-scale star formation. A third unresolved issue is the timing and drivers of cosmic reionization. The universe transitioned from neutral hydrogen to an ionized state between roughly 400 million and 1 billion years after the Big Bang. The sources that powered this transition remain debated. Conventional calculations struggle to produce enough ionizing photons from early galaxies alone, especially given uncertainties about the escape fraction of UV radiation. Dark stars, despite cooler surfaces than massive fusion stars, can be extremely luminous due to their size. Some models suggest their output could meaningfully contribute to reionization, especially if even a small population existed over a prolonged period. They wouldn't replace galaxies as reionization engines, but could supplement them in ways that reduce strain on early galaxy models. Chemical evolution introduces another clue. Some extremely metal-poor stars in the Milky Way halo appear to carry unusual abundance patterns that don't line up cleanly with yields from standard POP3 supernovae. While not direct evidence for dark stars, such mismatches point to the complexity of the early chemical environment. If some early massive objects collapsed without producing metal-rich ejecta, precisely what a collapsing supermassive dark star would do, this would alter metallicity patterns in ways that might echo through later generations. Taken together, These puzzles form a coherent structure of missing pieces. Early black holes too massive, early galaxies too bright, reionization too early and energetic, chemical signatures not fully accounted for. Each problem has conventional proposed solutions: direct collapse black holes, starburst episodes, exotic initial mass functions, but none is fully settled. Dark stars don't replace these explanations. Instead, they offer an alternative route that naturally threads through many of the gaps at once. They provide a physically consistent mechanism for early heavy black hole seeds, anomalous brightness, and long-lived luminous sources without requiring extreme assumptions about galaxy formation efficiency. This is why the dark star hypothesis matters. It is not an attempt to rewrite cosmic history for dramatic effect. It is a response to real, empirical inconsistencies. When a single theoretical construct can address multiple outstanding problems, and when observations reveal unexpected candidates that roughly match its predictions, the idea graduates from speculative to testworthy. And that is the stage at which JWST found the universe, waiting for data precise, enough to confirm or refute an audacious but coherent hypothesis. The gaps in the early cosmos were already whispering. JWST arrived just in time to listen more closely. When the James Webb Space Telescope finally unfolded its segmented mirror and cooled its instruments to operational temperatures, it became the first observatory capable of routinely accessing the epoch where dark stars, if they ever existed, would shine. JWST's design isn't just an upgrade over Hubble. It's an entirely different class of instrument, optimized specifically for the wavelengths where the earliest cosmic light now resides. Because of cosmic expansion, photons emitted in the ultraviolet by the first luminous objects are stretched into the infrared by the time they reach us. Hubble, with its limited infrared reach, could sense hints of these ancient sources but not dissect them. JWST, with its powerful suite of infrared images and spectrographs, was built to do exactly that. The key to JWST's capability lies in how it reads ancient light. Instruments like NIRCam capture faint, redshifted sources across broad fields, identifying candidates that might lie at enormous distances. But the truly transformative tool is NIRSpec, JWST's near-infrared spectrograph. Unlike simple imaging, spectroscopy breaks incoming light into distinct wavelengths, revealing detailed information about temperature, elemental composition, ionization state, redshift, and energy distribution. It is through these spectral fingerprints that astronomers can distinguish a young galaxy from a single massive object, a fusion-driven star from something fueled by a more exotic energy source. Ancient light is challenging to pass. Objects at redshift 10, 12, 14, and beyond are faint, smeared across wavelengths distorted by billions of years of cosmic evolution. Dust, gas, intervening galaxies, and gravitational lensing complicate the interpretation. A candidate may appear bright not because it is intrinsically luminous, but because a foreground galaxy magnified it. Or a spectral line may mimic one expected from helium or hydrogen, when it is actually produced by a different process entirely. JWST's sensitivity, however, moves these uncertainties into a regime where they can be disentangled rather than simply acknowledged. This observational precision matters because dark stars, if they exist, would have unique signatures. Their massive radii and cool surface temperatures would give them characteristic spectral slopes different from compact, hot POP3 stars. Their lack of metals would produce a clean, primordial spectrum. Their luminosities could be high enough to mimic small galaxies. And certain helium features, particularly the He2 1640 angstrom line, could emerge in ways not expected from standard stellar populations. Before JWST, none of these properties could be reliably measured at the distances where dark stars would be found. After JWST, they can be. This is why astronomers immediately pointed JWST toward deep fields designed to probe the earliest epochs. Surveys like JADES, JWST Advanced Deep Extragalactic Survey were crafted to map galaxies, star-forming regions, and any unusual objects populating the universe's first few 100 million years. Because JWST can observe multiple targets simultaneously with NIRSpec's microshutter array, it can gather spectra for dozens of faint ancient objects in a single pointing, something no previous instrument could do at this redshift. The telescope's earliest deep observations revealed a cosmos far more crowded and luminous than anticipated, with galaxies forming earlier and growing faster than predicted. That was already surprising. But embedded among those distant smudges of light were several objects whose brightness, spectral shape, and inferred size didn't match the typical profile of young galaxies. These anomalies became the perfect testbed for hypotheses like dark stars, which had been waiting for data precise enough to evaluate them. JWST didn't set out to find dark stars, but by providing access to the universe's infancy with unprecedented clarity, it opened a window where such exotic objects, if real, would finally reveal themselves. The first systematic search for unusual, high redshift objects began within the JADES program, a deep field campaign designed to map galaxies in the first few 100 million years of cosmic history. JADES uses JWST's NIRCam to identify promising distant targets and then funnels them into NIRSpec's microshutter array for detailed spectroscopy. This approach is powerful because it doesn't rely solely on brightness or morphology. It extracts the physical fingerprints embedded in the light itself. When the JADES team analyzed their earliest NIRSPEC results, 4 objects immediately stood apart from the rest, not because they were the brightest, but because they didn't behave like ordinary galaxies or conventional stars. The 4 candidates were designated JADES GSC 11-0, JADES GSC 13-0, JADES GSC 14-0, and JADES GSC 14-1. Their redshifts placed them between roughly 300 and 450 million years after the Big Bang, making them among the most ancient light sources ever observed. At these distances, nearly everything we see should be either small protogalaxies or compact star clusters beginning to form the first chemically enriched populations. Instead, these 4 objects exhibited spectral shapes and luminosities that didn't fit neatly into the templates expected from such systems. The first surprise was their luminosity. Each candidate was brighter than typical early galaxies of comparable mass, and in some cases bright enough to be confused for multi-source complexes. But NIRSpec's spectra indicated the light was not obviously composed of multiple distinct stellar populations. Instead, the spectral energy distribution of each candidate fit reasonably well with the model of a single, massive, metal-poor body. This is unusual because galaxies, even infant ones, produce complex spectra with blended features from varying star ages, dust absorption, and ionized gas emission. These 4 did not. Their profiles were clean, smooth, and lacked the metal lines typically expected from even minimal stellar processing. The second surprise came from their apparent sizes and temperatures. When researchers modeled the spectra, they found that the inferred sizes could be enormous. Too large for compact stellar clusters, too large for typical star-forming knots, yet still consistent with predictions for supermassive dark stars. Their estimated surface temperatures were cooler than those of the hottest population of fusion-driven stars, but still compatible with a luminous, inflated object powered by a non-fusion mechanism. In particular, their colors and slopes in the infrared bands aligned with models of objects that are extremely bright, but not dominated by the blistering ultraviolet radiation characteristic of massive fusion stars. The third surprise came from comparisons with dark star theoretical templates. The teams involved ran simulations that included known dark star parameters: large radii, cool surfaces, lack of metals, and distinctive luminosity curves. Remarkably, each of the four candidates could be matched to a dark star model within plausible parameter ranges, especially under the supermassive dark star framework, where masses can reach hundreds of thousands or even millions of solar masses. These matches didn't prove the dark star hypothesis, but they did demonstrate that the candidates are consistent with dark star expectations in a way few other hypothetical structures are. What strengthened the case further was the fact that no single conventional explanation fit all four objects cleanly. Young galaxies? Perhaps, but then their spectra should show some degree of complexity. Fusion-powered, supermassive primordial stars? Possibly, but those typically produce more extreme ultraviolet signatures. Gravitational lensing? A viable concern, but modeling suggested insufficient lensing magnification in these specific sightlines. Instrumental artifacts? Always a possibility, but unlikely across multiple independent, well-calibrated spectra. By the time the data were published, researchers realized they had stumbled onto a small population of anomalous ancient luminous sources, objects that looked just plausible enough to be dark stars that the idea could no longer be ignored. The dark star hypothesis had waited more than a decade for observations of this precision. Now, suddenly, 4 candidates appeared in a single survey. Of course, a match to theoretical templates is not confirmation. It is an invitation, a hint that the cosmos might be more complicated than expected, and that JWST in its first deep field campaigns had delivered a dataset rich enough to test radical ideas. Each candidate raised new questions. Is the light coming from a single object or an unresolved cluster? Are we seeing exotic stellar physics, or the earliest examples of structures that defy traditional categories? Is dark matter revealing itself indirectly through the light of a star that shouldn't exist? These questions pushed researchers toward the next step, searching for spectral signatures that could decisively distinguish a dark star from a massive fusion-powered primordial object. And in one candidate, Jade's GSZ140, something remarkable emerged. Among the 4 anomalous Jade's objects, Jade's GSZ14-0 quickly became the centerpiece of the investigation because its spectrum contained something that, at first glance, looked like the long-predicted fingerprint of a dark star. When NIRSpec broke apart its ancient light, researchers identified a feature consistent with a singly ionized helium signature, specifically the He2 line, that, after. Correcting for the object's extreme redshift corresponds to the well-known 1640 angstrom absorption feature. This stood out immediately because the He2 1640 line has long been discussed in theoretical literature as one of the few potential observable markers of dark stars or other exotic, metal-free, extremely hot early sources, standard early galaxies, especially those composed of mixed, fusion-powered stars, are not expected to produce an isolated helium absorption feature of this kind without accompanying metal lines or other indicators of intense nebular emission. The detection was tentative but intriguing. In dark star models, the He2 signature can appear because the star's inflated size, low surface gravity, and unusual temperature profile create atmospheric conditions that allow helium ionization without the extreme ultraviolet output that would normally ionize surrounding gas clouds. As a result, a dark star can display helium features while still lacking the high ionization metal lines that accompany massive fusion stars. This makes the He2-1640 line a potential, though not guaranteed, flag for a dark matter-powered object. When researchers compared the observed spectral profile of JWST's 14-0 against their template library, they found that dark star atmospheric models provided a surprisingly good match across several wavelength ranges. However, the promise of a smoking gun dimmed as additional data arrived. Follow-up observations using the Atacama Large Millimeter/Submillimeter Array ALMA suggested the presence of faint oxygen emission, specifically O3 lines, signals that should not exist in a pure hydrogen-helium object. Oxygen can only be created through nuclear fusion inside massive stars or supernovae, meaning its presence implies that at least some traditional star formation occurred in or near the source. This runs directly against the most restrictive dark star models, which predict metal-free atmospheres. If the oxygen detection is correct, and there is still debate due to the challenges of interpreting faint, high redshift ALMA lines, then the object might be better explained as a supermassive primordial star or a compact early galaxy containing extremely hot metal-poor fusion stars rather than a dark matter-powered giant. The ambiguity doesn't end there. Some teams argue that the He2 feature itself may not be as clean or isolated as initially believed. At these redshifts, spectral resolution is pushed to its limits, and small variations in noise, modeling assumptions, or background subtraction can mimic or distort helium lines. Others point out that exotic fusion-powered objects, such as massive, metal-free population 3 star clusters, can also produce He2 signatures under some conditions, especially if they contain extremely hot, short-lived stars on the upper end of the mass spectrum. This leaves the community in a state of cautious tension. On one hand, Jade's GSZ 14-0 is among the brightest and most distant objects ever observed, and its spectral shape genuinely resembles dark star models more closely than traditional galaxies. On the other hand, the possible oxygen detection complicates any simple interpretation, and the spectral data are not yet of sufficient quality to decisively separate dark stars from more mundane explanations. The object occupies an uncomfortable middle ground, too bright, too smooth, too metal-poor to be easily dismissed as an ordinary early galaxy, yet too ambiguous, too noisy, and potentially too chemically enriched to claim as a dark matter-powered star. The result is neither a slam-dunk discovery nor an easy refutation. It is the very definition of cosmic ambiguity, a signal tantalizing enough to provoke serious debate, but still fragile enough to collapse under scrutiny. The situation highlights a sobering truth about frontier astronomy. Sometimes nature does not provide clean answers, only hints and half-formed shadows in the data. In Jade's GSC's 14-0, we see the outline of something unusual. Whether that outline traces the silhouette of a true dark star or the blurred form of a more conventional object distorted by distance, noise, and cosmic evolution remains an open question. JWST has delivered the first clues, but the verdict will require spectroscopy with higher resolution, deeper exposures, and multi-instrument confirmation. For now, the smoking gun is neither smoking nor a gun, just a shimmer in ancient light, daring astronomers to look closer. Skepticism grew quickly once the initial excitement settled, because even though the dark star hypothesis fits some of the anomalies JWST uncovered, it also carries substantial theoretical baggage. Many astrophysicists argue that before invoking an exotic new class of star, every conventional explanation must be stretched to its breaking point, and, in their view, that threshold has not yet been met. The criticisms come from multiple angles: stellar evolution, dark matter physics, observational interpretation, and statistical likelihood. Each line of critique chips away at the seemingly elegant picture of dark stars and reveals how difficult it would be for such objects to form, persist, and remain observable. The first major critique concerns metallicity, which has emerged as one of the most contentious issues. Dark stars, by definition, must have zero metals: no oxygen, no carbon, no heavy elements at all. They are supposed to be pristine relics of untouched hydrogen and helium. That's why the possible detection of oxygen in JWST's 14-0 set off alarms. Even a tiny amount of oxygen implies fusion occurred, somewhere, somehow. Fusion means massive stars lived and died nearby or inside the object, contaminating the gas with supernova products. If metals are present, the object cannot be a pure dark star. Critics argue this alone is enough to challenge the dark star interpretation, unless the oxygen detection turns out to be a misidentification or contamination from a foreground source, neither of which can be ruled out yet, but neither of which is assumed by default. The second critique focuses on formation likelihood. Dark stars require very specific conditions: extremely dense, centrally concentrated dark matter in early mini-halos, baryonic collapse that drags dark matter inward without fragmenting into multiple star-forming clumps, and annihilation rates high enough to counteract gravitational collapse. According to many simulations, this parameter space is narrow. It exists, but only under finely tuned circumstances. What's more, dark matter annihilation heating must dominate over cooling just long enough, and uniformly enough, to inflate the star without triggering fusion. Astrophysicist Daniel Whalen and others argue that such conditions may occur rarely, if at all, and that even if dark stars do form, they could be too few, too brief, or too faint to be detected at the distances JWST is probing. Another concern involves dark matter particle physics, particularly the assumption that the dark matter involved would be WIMPs with annihilation cross-sections in the right range to heat a forming star. This is not a settled issue. WIMPs have evaded every major direct detection experiment to date. If dark matter is not a WIMP, or if its annihilation cross-section differs significantly from expectations, dark stars may not form or may not be luminous enough to survive for long. The whole existence of dark stars depends on particle physics that remains unconfirmed. A fourth line of skepticism centers on lifetime and stability. Even if dark stars form, how long can they actually last? Some theoretical models propose lifetimes of millions of years or more, but others show that once captured dark matter is exhausted, either by annihilation or by changes in the halo's density profile. The star collapses quickly, failing to reach supermassive scales. In these models, the inflation phase is short-lived, making detection at redshifts above 10 extremely unlikely. Critics argue that finding 4 candidates in the first JADES field would require dark stars to be far more common and longer-lived than most theoretical calculations allow. A final layer of skepticism concerns interpretation bias. JWST has revealed that early galaxies are brighter than anticipated, which can make them resemble exotic objects simply because existing models underestimated star formation efficiency in the early universe. Several teams suggest that the simplest explanation for the JADES candidates might be supermassive primordial stars, fusion-driven objects far more massive than anything observed locally, but still well within the realm of baryonic physics. These stars could produce He2 signatures, extreme luminosities, and metal-poor spectra without requiring dark matter heating. The early universe was a chaotic and rapidly evolving environment. Powerful bursts of star formation could produce objects that superficially mimic dark stars without invoking exotic processes. Taken together, these critiques form a coherent counterargument. Dark stars are possible in theory, but improbable in practice. The candidates JWST found could easily be explained by rare but conventional astrophysical processes: supermassive fusion stars, dense star clusters, or compact early galaxies undergoing extreme starbursts. Until the data become more precise, skeptics argue that invoking dark matter-powered stars is premature. Still, even skeptics admit that the candidates are unusual. They sit at the boundary between known physics and new territory, forcing cosmologists to re-examine the assumptions embedded in early universe models. Whether they turn out to be dark stars or not, their existence reminds the scientific community that the first billion years of cosmic history remain only partially understood, and that some mysteries will resist explanation until better data arrive. The theoretical scaffolding behind dark stars was built long before JWST ever saw them, and much of it comes from simulations that tried to answer a deceptively simple question: what happens to a primordial gas cloud when dark matter is not just present, but actively releasing energy? Early computational work by Frese, Spoglia, Gondolo, and others laid the foundation, but subsequent generations of simulations expanded the idea into a diverse family of possible stellar structures. These models explored not just the initial formation process, but also how such stars might grow, stabilize, radiate, and ultimately die. Each new layer of modeling revealed additional complexities and additional uncertainties that defined the current theoretical frontier. At the core of these simulations lies the physics of adiabatic contraction. As the baryonic gas collapses into the center of a dark matter mini-halo, it deepens the gravitational potential and pulls dark matter inward with it. This steepens the density profile in the core. Because annihilation heating scales with the square of dark matter density, the central region becomes a concentrated power source. Early simulations showed that under the right conditions, this heating halts further collapse, stabilizing the protostar before temperatures rise high enough to ignite nuclear fusion. Instead of a compact core, the forming object becomes an inflated, diffuse sphere, a dark star, whose internal equilibrium depends on the continuous interplay between annihilation heating and radiative cooling. Yet, as models became more detailed, it became clear that dark stars are not a single type of object, but a spectrum of possibilities shaped by uncertain particle physics and environmental conditions. Some simulations produced small dark stars, tens to hundreds of solar masses, relatively short-lived, unable to grow beyond the mass range of conventional massive stars. Others, however, yielded supermassive dark stars, growing to 100,000 or even several million solar masses. These giants can form if dark matter density remains high for extended periods, and if baryonic accretion proceeds efficiently. In such models, dark stars effectively become luminous black hole precursors, giant diffuse envelopes surrounding a dark matter-fueled core. A key branch point between models involves whether dark stars rely only on the initial concentration of dark matter or whether they can continuously capture dark matter particles as they evolve. The latter requires WIMPs to scatter elastically with baryons, a property that depends on specific interaction. Cross-sections that remain unconfirmed in laboratory experiments. If capture is efficient, dark stars can live much longer and grow much larger. If capture is inefficient, the initial supply of dark matter is quickly depleted and the star collapses before reaching supermassive scales. These two regimes, capture-dominated and depletion-dominated, produce dramatically different predictions, and current particle physics constraints make it difficult to determine which regime, if any, reflects reality. Modeling the extended atmospheres of dark stars introduced another layer of complexity. Because dark stars are so large and diffuse, their surface temperatures are relatively low, often a few thousand Kelvin. But their total luminosity can still rival small galaxies. This combination produces unusual spectral energy distributions, bright in infrared wavelengths, weak in the ultraviolet, and lacking the metal lines that characterize even the earliest fusion-driven stars. Yet atmospheres this vast and tenuous are challenging to simulate. Uncertainties in opacity, convection, and radiation transport can shift predicted spectra enough to overlap with those of other exotic early universe objects, making observational distinctions subtle and model-dependent. Another major challenge lies in modeling the collapse phase, the moment when dark matter heating can no longer support the star. Once annihilation rates fall, the object loses equilibrium and collapses under its own gravity. In simulations where dark stars reach supermassive sizes, this collapse can seed black holes of 10 to the power of 4 to 10 to the power of 6 solar masses, providing a natural route to the supermassive black holes seen at high redshift. But collapse dynamics depend heavily on how mass is distributed within the star, the equation of state of the gas, and whether nuclear fusion ignites during the final contraction. Different modeling choices produce different outcomes, with some predicting a direct collapse and others predicting brief fusion phases before black hole formation. This diversity means that even if dark stars existed, their evolutionary pathways may not be uniform. Finally, simulations have to confront cosmological context. Dark stars don't form in isolation. They form within mini-halos, subject to mergers, turbulence, radiation feedback, and the growing complexity of early structure formation. Large-scale cosmological simulations that include dark matter heating are only beginning to be developed, and they show both promise and caution. The environmental conditions required for long-lived, supermassive dark stars may be rare, but not impossible. This leaves the door open, but only partially. Theoretical uncertainties remain large, and different computational groups obtain different formation rates depending on modeling assumptions. In summary, the theoretical frontier is rich, intricate, and deeply unsettled. Dark stars are not a monolithic prediction, but a branching tree of possibilities shaped by still unknown properties of dark matter, incomplete models of early gas dynamics, and the chaotic conditions of cosmic dawn. JWST has now produced candidates that seem to sit somewhere within the vast parameter space of dark star simulations. But which branch they inhabit, or whether they belong anywhere on the tree at all, remains unclear. The simulations provide pathways, not certainties, and the next step is determining whether nature actually followed any of them. If the dark star interpretation proves correct, the entire opening chapter of the universe undergoes a profound shift. Not a small revision, but a restructuring of how we think the cosmos transitioned from darkness to light. The conventional picture begins with fusion, dense clouds collapsing until hydrogen ignites, forming the first population 3 stars whose ultraviolet light reionizes the universe, seeds it with heavy elements, and paves the way for galaxies and black holes. But if dark stars existed, fusion would no longer be the first driver of cosmic luminosity. Instead, the earliest beacons would have been powered by dark matter itself, the universe's most mysterious component, shining not through thermonuclear fire, but through annihilation energy born from the physics of the invisible sector. This shift carries enormous consequences. First, it means the first luminous objects were fundamentally different, not compact, hot, short-lived fusion furnaces, but enormous, cool, diffuse giants glowing in infrared light. Their existence would redefine the timeline of first light. Instead of waiting for gas clouds to collapse tightly enough to ignite fusion, the cosmos may have glowed earlier, and under different physical principles than any standard model currently assumes. Rionization models, carefully calibrated to fusion-driven UV output, would require revision because dark stars emit differently, perhaps contributing to heating the intergalactic medium in ways not presently accounted for. Second, dark stars provide a natural solution to one of the thorniest early universe puzzles: the origins of supermassive black holes. If dark stars could grow to hundreds of thousands or millions of solar masses, their eventual collapse would instantly create massive black hole seeds. This bypasses the slow, inefficient pathway of growing black holes from ordinary, approximately 100 solar mass, POP3 remnants. The supermassive black holes detected at redshifts 7 to 10, some already exceeding 1 billion solar masses, become far easier to explain. The universe wouldn't need extreme accretion rates or improbable merger histories. Instead, it would simply recycle the corpses of its first and largest dark matter-powered giants. A third consequence concerns our understanding of dark matter itself. If dark stars existed, then dark matter cannot be an entirely inert gravitational component. It must interact with ordinary matter, at least weakly, through annihilation or scattering. This would be one of the first astrophysical signatures of dark matter beyond gravity. It would severely constrain the particle properties of dark matter, ruling out entire classes of candidates while favoring those capable of powering dark star heating. Essentially, dark stars would do what decades of underground detectors have not: provide concrete evidence of dark matter annihilation physics. Fourth, the cosmic chemical timeline changes. In the standard scenario, the first supernovae come from population 3 stars, enriching their environments with heavy elements that enable complex chemistry and later star and planet formation. But if some early objects were dark stars, they would not enrich their surroundings in the same way. Supermassive dark stars that collapse directly into black holes skip the supernova phase entirely, injecting no metals into space. This would delay chemical evolution in some regions, altering the distribution of primordial metal-poor gas and potentially creating pockets of the universe where fusion-based star formation took longer to begin. Dark star-dominated regions might host a uniquely different lineage of early structures. Fifth, the notion of a first generation of stars changes meaning. Instead of a single homogeneous population of metal-free fusion-driven giants, the universe may have launched with 2 parallel families: conventional POP3 stars and exotic dark stars. Their coexistence would create an early cosmic environment more diverse and dynamic than previously imagined. Some patches of the early universe might have been dominated by dark star glow, others by the fierce UV radiation of massive fusion stars. The interplay of the two would shape ionization fronts, gas cooling pathways, and the emergent architecture of early galaxies. The narrative impact is as dramatic as the scientific one. If dark stars are real, then the universe's first light didn't come from fire. It came from shadow. The energy that illuminated cosmic dawn would have come not from nuclear reactions familiar to us, but from the annihilation of particles belonging to the unseen. 85% of matter in the cosmos. The first cosmic beacons would not resemble the sun or any familiar star. They would be monstrous, ghostly, and powered by physics that remains experimentally unconfirmed. Humanity would have spent decades looking for dark matter in laboratories, only to discover that its first and most dramatic signatures were written across the sky 13.8 billion years ago. Even our philosophical relationship to cosmic history shifts. Much of modern astrophysics is built on the idea that the universe behaves consistently across time. Gravity collapses clouds, fusion lights stars, stars explode, galaxies form. Dark stars would reveal that the early universe was far stranger, governed not only by the familiar processes we test in labs, but by exotic interactions that may have played a central role only during the universe's first few 100 million years. They would represent a moment when dark matter was not merely a background actor, but the dominant driver of luminous structure. If true, dark stars rewrite the origin story, not replacing the old framework, but expanding it into something deeper, broader, and more mysterious. The universe's first chapter would become a tale not of fire, but of annihilation. Not of familiar atoms, but of unseen particles shaping light itself. And that revelation would echo across cosmology, from the birth of black holes to the nature of dark matter to the architecture of the cosmic web. The deeper astronomers dug into the JWST data, the clearer it became that the evidence was speaking, but only in the faintest murmur. None of the 4 anomalous candidates offered a clean, decisive signature. Instead, each object presented a mixture of signals, some aligning neatly with dark star predictions, others drifting toward more conventional explanations. The result was a scientific stalemate, where every dataset illuminated one possibility while simultaneously casting shadows across another. The first ambiguity lies in spectral precision. JWST's NIOSPEC is extraordinarily powerful, but at redshifts beyond 10, the photons arriving at the detector are stretched, faint, and sparse. Noise levels climb. Sky contamination becomes harder to subtract, and even small uncertainties in continuum fitting can distort faint absorption features. This is exactly the regime where helium lines or subtle spectral slopes might appear, and exactly where they are most difficult to interpret reliably. Many features that seem promising at low signal-to-noise fade into statistical ambiguity when reanalyzed pixel by pixel. Second, the luminosity profiles of the candidates are striking, but not definitive. Dark stars can be extremely bright, but so can compact primordial star clusters or star-bursting proto-galaxies with unusually top-heavy stellar populations. JWST's angular resolution at such distances is insufficient to resolve structures smaller than a few hundred parsecs, meaning a tightly packed cluster of massive fusion stars could masquerade as a single inflated object. The smoothness of the spectra argues for a single source, but the resolution is not quite high enough to conclusively rule out multiple unresolved stars. What appears to be a gargantuan, dark matter-powered object may instead be a population of ordinary, if extreme, early stars packed tightly enough to blend their light into one. Third, even the redshift measurements, while robust, come with caveats. Spectroscopic redshifts are solid when clear lines are present, but in metal-poor, line-sparse objects, Redshift often relies on break features, the Lyman break, Balmer break, or continuum drop-offs, that can shift depending on dust, temperature, and model assumptions. A misestimated redshift by even a few percent can move an object in or out of the expected regime for dark star formation, affecting both luminosity and size calculations. The candidates still lie at extraordinary distances, but the exact redshift matters more than usual because theoretical dark star windows are tightly constrained in cosmic time. Fourth, the oxygen question continues to cast a long shadow. ALMA's evidence for O3 in JADE's GS as 14-0 remains controversial, partly because detections at this redshift are near the threshold of the instrument's capabilities. Some analysts argue that the oxygen line matches expectations for an emission feature at the reported redshift. Others contend that the feature's significance drops below detection thresholds when alternative noise models are used. If the oxygen is real, it challenges the dark star interpretation. If it is not, the helium feature regains importance. But the current data are too thin to favor one interpretation decisively. Beyond individual lines, the statistical rarity of the candidates raises questions. JWST's deep fields contain thousands of early objects. Finding 4 plausible dark star analogues in such a small patch of sky might imply that dark stars were common, far more common than many simulations predict. That raises suspicion. Either dark stars are easier to form than theory suggests, or these objects belong to a population of extreme but conventional sources. The early universe simply produced in greater numbers than expected. In either case, the rarity or abundance itself becomes an inference built atop uncertain data. Even the researchers behind the discovery remain cautious. Their published work emphasizes plausibility, not confirmation. The models fit, but they fit imperfectly. The spectral features align, but not cleanly. The luminosities match predictions, but alternative explanations remain viable. In their own words, the evidence is suggestive, but not conclusive. And they explicitly call for higher resolution follow-up observations before drawing any firm conclusions. This is the uncomfortable truth of early universe astronomy. At the frontier of observation, the cosmos does not shout. It whispers. Every photon is precious. Every noise spike a potential mirage. Every interpretation a balance of probabilities. Signals emerge only through patience, careful analysis, and the willingness to entertain multiple competing explanations at once. So for now, the data offer no definitive declaration, no triumphal announcement, no breakthrough beyond dispute. Instead, we have a handful of objects that look like they could be dark stars, but could equally be something else. The universe is hinting at a possibility, not revealing a certainty. The clues are scattered, faint, and incomplete. They tell a story, but only in fragments. And the most tantalizing part is that those fragments are just clear enough and just strange enough to keep the dark star hypothesis alive. The more attention the dark star candidates received, the louder the chorus of caution grew. Astrophysicists who specialize in early universe structure formation, stellar evolution, and spectral modeling began weighing in, and many of them argued that the simplest explanations were being overshadowed by excitement for an exotic one. Their doubts weren't dismissive. They were methodical, grounded in decades of modeling experience, and focused on the principle that extraordinary claims require extraordinary evidence, especially when dealing with observations at the very edge of what our instruments can detect. One of the central objections comes from researchers like Daniel Whalen, whose work on primordial star formation suggests that the JADES candidates are far more naturally explained as supermassive primordial stars. These are fusion-powered, metal-free giants formed from the first gravitationally collapsing gas clouds. In Whelan's modelling, such stars can reach hundreds of thousands of solar masses, shine intensely, and display spectral slopes that superficially resemble those predicted for dark stars. Crucially, they would exist without requiring dark matter annihilation. To skeptics, invoking exotic dark matter physics is unnecessary when baryonic physics alone can produce similarly luminous early objects, especially at a time when the universe was dense, violent, and forming massive structures rapidly. Another criticism centers on metallic signatures, especially oxygen. Even if the ALMA oxygen detection in JADES GSZ 14-0 is marginal, its mere possibility alters the interpretation of the entire sample. Metals imply prior stellar evolution, massive stars living and dying, injecting enriched material into the surrounding medium. This contamination should not appear in a pristine, dark matter-supported star. Critics note that while the dark star hypothesis can accommodate some environmental complexity, it cannot tolerate metals within the star itself. If oxygen is real, the object cannot be a dark star. Skeptics argue that the presence of any metals anywhere in the immediate system strongly favors a young galaxy or star cluster rather than an isolated, metal-free monster. Then there's the statistical problem. Most simulations predict that dark stars, if they form at all, should be extremely rare. They require specific fine-tuned conditions, a mini-halo with just the right density profile, a collapsing gas cloud that remains monolithic instead of fragmenting, dark matter with annihilation, properties within a narrow theoretical window and a long enough period of stable feeding to reach supermassive scales. Yet, in the very first deep field JADES observed, 4 plausible candidates appeared. To critics, this abundance strains credibility. Either dark stars are far more common than current theory allows, which would require rethinking dark matter physics entirely, or the candidates belong to a population of extreme but conventional objects that JWST is only now able to reveal. Another deep concern involves dark matter capture, an element required by some versions of the dark star hypothesis. For a star to maintain annihilation-driven luminosity over long timescales, it must continuously capture dark matter particles as it grows. But whether dark matter scatters off baryons at rates sufficient for this process is unknown, and current direct detection experiments have not observed such interactions. Some theoretical models even suggest that if WIMP capture were efficient enough to power dark stars, it should already have produced detectable signals in underground detectors. Because no such signals have been observed, many physicists argue that dark stars requiring long-term capture cannot exist unless dark matter behaves differently from all current expectations. On top of these criticisms lies the broader issue of interpretation degeneracy. At extreme redshifts, many different physical objects can produce similar spectral shapes. Star-bursting proto-galaxies, dense clusters of population 3 stars, direct collapse black hole precursors, or even gravitationally magnified sources. Each of these scenarios has been shown, through modeling, to reproduce some aspects of the JADES spectra. Critics argue that unless JWST uncovers a spectral signature that cannot be mimicked, something unique to dark stars, the hypothesis remains vulnerable to more mundane interpretations. Even the helium signature, the most tantalizing hint, has been questioned. Some experts point out that He2 1640 can arise in very hot fusion-driven stars or in regions where gas is shock ionized. Others worry that the detection lies near the edge of NIRS-PEC's noise envelope, leaving room for misidentification. Without cleaner, higher resolution data, skeptics consider the helium absorption feature an interesting but insufficient clue. This convergence of objections doesn't kill the dark star hypothesis outright, but it places it in a precarious place. To many astrophysicists, dark stars are still viewed as a speculative idea that gained visibility primarily because JWST's discoveries were stranger and brighter than expected. They argue that early universe astrophysics is already full of extreme objects, hypernovae, massive pop-3 stars, direct collapse black holes, and that the burden of proof lies squarely on the exotic explanation, not the conventional ones. The skeptic's message is clear. The dark star hypothesis is fascinating, even beautiful, but beauty is not evidence. Until ambiguous signals sharpen into decisive signatures, skepticism remains the rational stance. The universe often offers misleading mirages at the cosmic horizon, and scientists are trained to proceed cautiously, especially when the data whisper rather than shout. With the first wave of JWST deep field observations exposing a handful of candidates that straddle the boundary between normal astrophysics and something far stranger, the next phase of the search now shifts from detection to discrimination. The central question is no longer, could these objects be dark stars, but rather, what observations could confirm or eliminate that possibility decisively? This reframing drives nearly every research proposal now aimed at cosmic dawn. If dark stars are real, their signals must be separable from those of supermassive primordial stars, dense star clusters, or compact protogalaxies. And if the candidates JWST has found aren't dark stars, then the telescope must search even deeper or more precisely to evaluate whether any such objects exist at all. The first and most immediate step involves higher resolution, longer exposure spectroscopy of the 4 JADES candidates. JWST can revisit these objects, locking NIRSpec onto their positions with deeper integrations that reduce noise and sharpen ambiguous features. A cleaner view of the He-1 diameter 640 feature, whether it exists, its depth, and whether it's accompanied by nearby continuum structures, could strongly shift the likelihood in one direction. If the oxygen line detected by ALMA in JADES GSZ's 14-0 is real, deeper JWST spectra should pick up weak associated metal lines. Conversely, if those metals truly are absent, the oxygen line may have been noise, a foreground contaminant, or misattributed. Clarifying this single point would simplify the interpretation of the entire sample. Parallel to JWST's efforts, ALMA follow-up observations are planned and, in some cases, already underway. ALMA's sensitivity to faint sub-millimeter emission lines, especially OP3 88 micrometers, makes it a powerful complementary tool. Its detections are currently marginal, but deeper exposures could either confirm metals decisively or rule them out. If even one candidate shows clear metal contamination, it moves off the dark star table. Conversely, a clean metal-free spectrum would elevate that candidate immediately as a serious dark star possibility. Beyond re-examining the original sources, researchers are broadening their search across new, deep field regions. JADES was just the beginning. Programs like Cosmos Web, SEERS, Primer, and Panoramic are probing different patches of sky with different depths and observing conditions. If dark stars exist at observable frequencies, they should appear in these surveys as well, possibly with even cleaner spectra or in environments offering less foreground interference. Finding more candidates would tell us whether the initial 4 were anomalies, statistical flukes, or part of an underlying population. Conversely, finding none would add weight to the interpretation that these first detections were exotic but conventional objects, rather than evidence of a new stellar class. Another branch of the search focuses on spectral modeling improvements. Existing dark star templates were built on idealized atmosphere models and simplified assumptions about opacity, convection, and radiative transport in ultra-large stellar envelopes. New computational efforts aim to generate more realistic, higher fidelity spectra that include full radiative hydrodynamic effects. These updated predictions may sharpen the spectral differences between dark stars and fusion-powered primordial giants. If the theoretical expectations become more precise, the ambiguous features in current data could become interpretable in ways they are not today. There's also growing interest in using time-domain observations. Dark stars, being massive and diffuse, might evolve in brightness differently than compact fusion stars. Their luminosity could vary slowly as dark matter heating fluctuates or as baryonic accretion changes. JWST's repeat observations over months or years could detect such slow variability, tiny shifts in brightness or spectral slope. That would be unusual for early galaxies, but plausible for an exotic, internally powered giant. Meanwhile, several research groups are exploring whether gravitational lensing surveys could amplify dark star signatures. A dark star lying behind a massive lensing cluster would be magnified enough for JWST to see details that would otherwise be out of reach. In fact, some of the earliest claims about extremely distant objects came from lensing surveys using Hubble. Now, JWST's ability to pair lensing magnification with deep infrared spectroscopy makes lensing fields prime hunting grounds for rare, exotic objects. Another frontier lies in multi-observatory synergy. As new facilities like the Nancy Grace Roman Space Telescope and the Extremely Large Telescope, ELT, come online, their capabilities will complement JWST. Roman's wide-field surveys could detect statistically significant populations of early candidates, while ELT's enormous collecting area will deliver ground-based spectra with resolutions far higher than JWST can achieve. A dark star candidate observed by all three, Roman for identification, JWST for infrared spectra, and ELT for high-resolution follow-up, would become a gold standard target. Finally, the search pushes deep into theoretical extensions. If dark stars exist, what is their abundance? How long do they live? What mass ranges are most likely? Could some survive into lower redshifts, appearing not only in cosmic dawn, but also in slightly later epochs, where observations are cleaner and brighter? If so, the search region expands. Dark star signatures might hide in places we have already surveyed, incorrectly classified as star clusters or unusual compact galaxies. This next phase is not just about confirmation, it's about mapping the possible space of early universe objects from the inside out. Even a null result, no dark stars after years of follow-up, would provide powerful constraints on dark matter physics, eliminating broad swaths of parameter space. And if even one object survives every test, no metals, a clean helium line, an inflated radius, a consistent spectral slope, then the cosmic origin story fundamentally changes. Astronomers now stand at a fork in the road. Deeper data could collapse the dark star hypothesis or elevate it into one of the most significant discoveries of the century. Either outcome will sharpen our understanding of the dawn of structure and the nature of the invisible matter that shapes the universe. When astronomers step back from the technical debates the statistical arguments, the line-by-line spectral analyses, a deeper realization emerges, one that touches not only astrophysics, but the human relationship with the cosmos. For more than a century, we have relied on a comforting assumption that the first light in the universe came from something familiar. Fusion is a process we understand intimately. We can reproduce it in laboratories, model it precisely, and observe it in stars across the sky. POP3 stars, the universe's first fusion engines, fit neatly into that framework. They made the darkness glow through a mechanism we recognize, a mechanism that seems almost inevitable given the known laws of physics. But the dark star hypothesis cracks that comfort open. It forces us to consider the possibility that the universe's earliest illumination came not from nuclear fire, but from dark matter, the very substance we still cannot see or detect directly. Imagine what that implies, that the cosmos itself may have begun by shining through a kind of physics we still only grasp through inference and gravitational footprints. The first light may have been born not from processes familiar to our laboratories, but from interactions occurring in a sector of nature we have never directly measured. Such a shift reshapes more than astrophysical models. It reshapes our philosophical narrative. Our story of cosmic dawn has always been one of continuity. Gravitational collapse leads to fusion. Fusion leads to starlight. Starlight leads to chemistry. Chemistry leads to planets. Planets lead to life. It's a linear chain, comforting in its familiarity. But if dark stars existed, the first link in that chain looks nothing like the ones that follow. The universe would have begun with a phase where dark matter, not ordinary matter, was in command of the light. The first beacons would have been quiet giants, diffuse and ghostly, glowing by annihilation rather than ignition. This raises uncomfortable questions. If we were wrong about the very first generation of luminous objects, objects that shaped the earliest cosmic structures, what else might we be wrong about? How many unquestioned assumptions about cosmic history are built on frameworks that simply worked? Well enough, given the data we had before JWST. The idea that the universe's initial light came from dark matter is a reminder that our understanding is always provisional, constrained not only by theory, but by the limits of our instruments. There is also a humbling philosophical symmetry here. Humanity has spent decades trying to detect dark matter directly, building underground detectors the size of buildings, deploying satellites, and constructing vast particle accelerators. And yet, the universe may have already given us colossal, dark matter-powered objects 13.8 billion years ago. Those giants may have lived, glowed, and collapsed long before the first nuclei formed the heavy elements needed for life. We were not there to witness them. The cosmos kept their existence hidden until our telescopes became sensitive enough to detect their faint whispers. There's a poetic irony in the idea that the first lighthouses in the universe might have been invisible in one sense, powered by particles we cannot see, emitting light we now struggle to interpret, but blindingly bright in another. They would have outshone entire protogalaxies, their radiance filling a newborn cosmos that had never known starlight. If dark stars were real, they would also force us to reconsider the notion of typicality. We often assume that the physics we see around us today, fusion stars, planetary systems, galactic structures, are representative of the cosmos across time. But dark stars would mark an era where the universe behaved fundamentally differently than it does now. It would be a reminder that cosmic history is not homogeneous. It may contain phases that are alien to our intuitions. The modern cosmos, with its familiar stars, may not be the rule, but the exception. And perhaps the most profound philosophical implication is this. If the earliest light came from dark matter, then the universe began with a contradiction: darkness producing light. Invisible matter, by annihilating itself, illuminating everything else. The metaphor writes itself, but in this context, it's not metaphor at all. It's physics. The realization is unsettling but beautiful. It suggests a cosmos far more mysterious than our current models reflect. A cosmos that has always contained layers we have not yet peeled back. Even now, with instruments as powerful as JWST, we are still only scratching the surface of what the early universe has to teach us. This zoom out doesn't give us answers, it widens the frame. It forces us to admit that cosmic dawn may not be a solved chapter, but a frontier. And it reminds us why we look up at all. Because the universe, even after 13.8 billion years, still has secrets vast enough to reshape our place within it. At this point in the story, everything converges: the discoveries, the doubts, the simulations, the spectra. We arrive at a crossroads where the evidence is tantalizing, but the interpretations diverge. The 4 JADES candidates sit at the center of this intersection, each one carrying clues that seem to point in opposite directions depending on how the light is read. Astronomers studying them find themselves oscillating between 2 realities: one where the dark star hypothesis survives the scrutiny of data, and another where the candidates fall neatly, perhaps too neatly, into the realm of extreme but conventional early universe objects. On one side of this crossroads stands the hopeful possibility. The helium feature in JWST's 14-0 remains intriguing. The candidates' spectral slopes still more closely resemble dark star models than they resemble typical galaxy templates. Their metal-poor nature, if metallicity truly is as low as some analyses suggest, fits the profile of primordial, non-fusion-driven bodies. The smoothness of their light curves hints that these objects may not be conglomerations of smaller stars. And the sheer fit of the models, the way dark star templates overlay their spectra with fewer discrepancies than most competing explanations, continues to stand out. For a theory that lived in mathematical margins for more than a decade, this is an extraordinary moment. The data, imperfect as it is, has finally produced objects that look like what dark star physics predicts. But on the other side stands the grounded skepticism. The possible oxygen detection in one candidate injects a toxin directly into the heart of the dark star case. The brightness of early galaxies, unexpectedly high across multiple surveys, suggests that astrophysics may simply need to revise its star formation efficiency models rather than invoke exotic new physics. Simulations of supermassive primordial stars, guided by conventional baryonic collapse, have grown more sophisticated and now reproduce many of the same observational features without needing dark matter annihilation. And the statistical oddity, the fact that 4 such objects appeared in the same early deep survey field, forces theorists either to assume dark stars are surprisingly common, or to confront the possibility that the candidates belong to a population of extreme, fusion-powered objects the early universe produced more frequently than anticipated. The crossroads is not symmetrical. One path, the dark star path, is narrower, riskier, and more fragile. It requires assumptions about dark matter that have no laboratory confirmation. It demands finely tuned early universe conditions that may exist only in theory. It must survive tests that grow more unforgiving as data quality improves. But it also offers a sweeping solution to multiple early universe mysteries: the rapid appearance of massive black holes, unexpected luminosities of early objects, and the potential for dark matter to leave its fingerprints on cosmic dawn. The other path, the skeptical path, is broader and feels safer. It leans heavily on established astrophysics, stretching but not breaking what we already know about massive stars, dense clusters, and extreme star formation episodes. It builds on familiar processes: gravitational collapse, fusion ignition, radiative feedback. This path requires fewer leaps, fewer assumptions, and fewer untested ideas. But it leaves certain puzzles unanswered, or forces them into more complicated conventional explanations. It solves the mystery of the Jade's objects without solving the larger enigmas of cosmic dawn. This is why the moment feels climactic, not because the evidence has reached a verdict, but because the debate cannot remain in equilibrium forever. Astronomy rarely stays in these liminal states for long. A single high-resolution spectrum, a cleaner detection of helium or metals, a time-domain brightness change, or a new candidate with unmistakably dark star-like features could tilt the balance decisively. One clear signal could validate the exotic or reinforce the mundane. But right now, we stand in the center of uncertainty. Data pushes from one side, doubt pulls from the other. Hope leans toward the extraordinary, caution leans toward the conventional. The scientific community is divided not in hostility, but in discipline. Every interpretation is weighed, every assumption interrogated, every alternative considered. This crossroads is where science is most alive. Not in certainty, not in conclusions, but in the struggle to reconcile curiosity with evidence. It is a moment when the universe whispers a possibility and humanity strains its instruments, its models, and its imagination to hear it more clearly. If dark stars are real, then we are witnessing the beginning of a paradigm shift, the rewriting of cosmic dawn. If they are not, then the process of refuting them will refine our understanding of early star formation, black hole seeding, and the physics of the earliest galaxies. Either way, the pursuit brings us closer to truth. But for now, we wait, we analyze, we debate, we prepare new observations, and we stand at the fork where two cosmic narratives diverge, unsure of which one the universe will choose. In the end, after the spectra have been analyzed, the models run, the debates sharpened, and the headlines faded, we're left with a quiet realization. The universe is under no obligation to make itself easy to understand. JWST has given us the most detailed glimpse of cosmic dawn in human history, and yet the objects we're staring at, these distant blurs of ancient light, remain wrapped in ambiguity. Whether they are dark stars, supermassive primordial stars, compact early galaxies, or something else entirely, they remind us that even with our most advanced tools, we are still outsiders looking in on a story 13.8 billion years in the making. There is something humbling in this. Humanity is observing light that has traveled across almost the entire age of the universe just to reach a telescope parked behind the moon. We can measure its wavelengths, model its origins, argue over its meaning, but we cannot make the cosmos answer us plainly. The candidates found in the JADE survey demonstrate this perfectly. Each one hints at something remarkable, yet none of them reveals its true nature without contradiction. Every spectral line is provisional. Every conclusion is conditional. Every explanation invites another question. And perhaps that is exactly as it should be. If cosmic dawn was simple, if the first stars were immediately obvious, if the universe offered clarity without resistance, then our role as explorers would be diminished. The beauty of astronomy lies not only in discovery but in pursuit. Dark stars, real or not, represent a possibility grand enough to expand our imaginations, yet grounded enough to challenge our scientific rigor. They push us to refine our instruments, update our models, and think more boldly about the physics that shaped the infancy of everything. The early universe was a place of extremes. Temperatures soared, densities fluctuated, and dark matter sculpted the scaffolding on which galaxies would grow. Whether dark stars flickered there or not, the fact that we can even pose the question is a triumph of human curiosity. JWST has extended our vision into epochs we once thought forever inaccessible. And in those epochs, the cosmos still manages to surprise us, with brightness where darkness was expected, with complexity where simplicity was assumed, with whispers where we hoped for declarations. In time, new observations will arrive. The candidates may be revealed as imposters, rare but conventional stars wearing the spectral masks of something stranger. Or perhaps new data will uncover a signature so clean, so unmistakable, that the existence of dark stars becomes undeniable. Either outcome enriches our understanding, either brings us closer to the truth. For now, the universe keeps its secrets. It allows us to glimpse its earliest moments, but not yet to decode them fully. It tempts us with anomalies, challenges us with ambiguity, and reminds us that the frontier of knowledge is always shifting. As we peer into the first billion years with instruments of extraordinary precision, we are confronted with a simple fact. The cosmos is vast, ancient, and far more intricate than any one theory can capture. Yet we continue to look. We continue to question. We continue to reach into the dark, searching for the origins of light. Because somewhere out there, hidden in the glow of distant galaxies, buried in the spectra of faint primordial objects, the universe may still be waiting to tell us the truth about its first stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.